This instructional video is intended to demonstrate the freezing point depression calculation of a saltwater solution, and that ties into the idea of colligative properties. The other side of this is, of course, boiling point elevation. So, question: how much salt would we need to add to water to achieve a freezing point of 0 degrees Fahrenheit? Well, the first step is to actually convert Fahrenheit to Celsius. So 0 degrees Fahrenheit is going to be equal to negative 17.78 degrees Celsius. We have our Fahrenheit to Celsius conversion, and because this is a colligative properties problem, we worry about the freezing point depression. So we have a formula that expresses how that works. So it's going to be the change in freezing temperature will be the freezing constant times the molality of the solute. So in this case, the molality is a type of concentration measure. The delta T is simply that final temperature change. And the Kf is a constant that depends on the identity of the solvent. In this case, it's water. So this is a constant. This is a value that we're looking for. So this is going to be the quantity that we'll need to solve for it. So our delta T, as found before, 17.78 degrees Celsius. Our Kf. We can look that up in a table, and what we have is 1.86 degrees Celsius kilogram per mole. So I'm going to now solve for the target molality. So the molality that we want will be the temperature depression divided by the constant. So that is 17.78 degrees Celsius divided by 1.86 degrees Celsius kilogram per mole. The degrees Celsius will cancel because our kilograms per mole are on the bottom. That's going to flip when we get up top, but we will now have our target molality. So that target molality is then going to be 9.56 moles of sodium chloride for every 1 kilogram of water. So that would be the end of the question, but if we're trying to be a bit more practical about it, then the next thing we want to do is convert the number of moles of sodium chloride to grams, because that's what we can measure out. And so this is a fairly standard mole conversion problem. So we need to know how many grams are in 1 mole. We would look through a periodic chart, add up the molar mass of sodium and chlorine, and we would get 58.35 grams per 1 mole. So we multiply these two, the moles cancel. What we're left with are grams. That gives us our final result of 557.8 grams of sodium chloride for each 1 kilogram of water. Now, that's how we would use the idea of colligative properties for freezing point depression to get a practical answer for this problem. And if we add this quantity of salt to our water in that ratio, we'll expect to see the freezing point be depressed by that much. Huh? Oh, right. I need me to finish this. So you just saw me do all of the calculations on the whiteboard, and now that was theory. It's time for the experiment. So I've got the calculations here that tell me however much mass of water I have, I'm going to need to add 55.78% of that mass in sodium chloride, aka regular table salt, to it to achieve a freezing point depression that will get us down to 0 degrees Fahrenheit Fortunately, I have salt that's actually just salt, kosher salt. If you read the ingredient list on this thing, it actually pretty non-sarcastically just says salt. So that's going to be the salt. I've got ice in the freezer, and the only other thing I need in order to do this as an experiment that has some reasonable amount of design is I'm going to need 2 identical glasses to put my ice and salt in. So I've got these here. I'm going to need a scale so I can weigh things out and do the calculations, and I'll use a nice ramekin as a weighing dish for the salt itself. Now the idea here is that we want to have as many confounding variables neutralized out as possible. So identical glasses solves that. Letting things come to temperature in the same space solves any issues with whether or not we're being fair with the temperature setting. Using a digital scale helps me in terms of making sure that I've got the appropriate amount of salt that I'm going to add to the ice and then have the glass without any salt in it whatsoever as a control. The important thing to think about here is that experimental design tries to take into account everything we've done in the theory, but we also want to eliminate any known problems that could ruin it. So we want to have as many other features as identical as possible, so that we're really only doing one thing at a time differently. And in this case, I'm going to have the same number of cubes of ice in both glasses. I'll take a mass measurement just to be sure, and then I'll take the 55.78% of that as the mass of salt that I'll be adding to one of them. At that point, I can then set them both aside and see if one melts faster than the other. So what we have here are the 2 identical glasses. I've put 4 ice cubes in, weighed it out, played around with it a bit, and they're 70 and 73 grams of ice. So based on that calculation, I've got 41 grams of salt to add. Now in principle, I'll add this here, and what we should see over time, I'll check back periodically and take pictures, etc. But what we should see is that the salted ice will have a lower freezing point, which means that it should start melting faster than the ice by itself. It'll melt faster and at a lower overall temperature. So I'm going to add that in, and we'll watch the science happen. For the record, this might take a minute or several. So I'll be popping in with periodic updates and pictures so that we can see what happens. These are side-by-side images of the heavily salted ice and unsalted ice in front of a timer so that you can tell how quickly one is melting versus the other. And as you'll soon hear, there are even some temperature differences in these 2 cases. So the regular ice and the heavily salted ice have been running for almost an hour, and there's definitely more melting on this side with the salted ice, but it's also significantly colder to the touch. Regular ice, still cold, right? It's ice water, but definitely not melted as much. So, what did we learn? Well, the heavily salted ice did melt quicker because the freezing point was lower, so that kind of kick-started the melting. But it maintained that lower temperature while it was melting compared to the temperature of the regular ice, unsalted ice. So the salted ice is effective at keeping a lower temperature overall while it's melting. And as a bonus, this has been sitting in my freezer for several hours since completing the experiment, and I've got a hunk of ice, which I'm assuming is all precipitated, not ice, salt. It's all precipitated out, but this salt water is not melting in a freezer, which tells me that the kitchen freezer has to be set at a temperature that's a little bit above that depressed freezing point. So, yay science, yay colligative properties. And looks like I can do experiments too. So that's an all-around win for the good guys.